Welcome back, traveler. Tonight we drift into emotion so familiar that it hides in plain sight. The moon pulls the oceans. The tides rise and fall. Beaches breathe in and out twice a day. It feels like one of those facts that belongs to childhood diagrams and vacation memories, not something that could still surprise you. Most of us imagine it as a simple tug. The moon pulls the water toward itself. The oceans swell, and the rest is just geography filling in the gaps. A quiet interaction between a distant rock and a restless sea. But here's what most people don't realize. The moon isn't pulling the oceans upward so much as it's pulling Earth apart. The water moves not because it's light, but because everything else resists. And the pattern that results isn't centered beneath the moon at all. Once you see that, a series of strange consequences begins to unfold. The ground beneath you is moving in response to something you can't feel. The timing of the tides depends on motion, not distance. The solid earth flexes along with the water, and the moon's influence reaches far beyond coastlines, quietly shaping the length of our days. By the end of this journey, you'll understand why tides form where intuition says they shouldn't, why the moon's pull slows Earth's rotation, and how a distant orbiting body can control an entire planet without ever touching it. If you're enjoying these late-night explorations, like the video, subscribe, and leave a comment telling me where you're watching from and what time it is. Now, let's begin. The easiest way to think about tides is to imagine the ocean as something separate from the planet, like a loose layer slushing on top of a solid sphere. The moon passes overhead, it pulls on that loose layer, and the water responds like it's being gently summoned upward. The coastline doesn't matter at first. The details don't matter at first. You get a clean picture. A distant object pulls. The sea rises. You can almost feel why the story stuck. Water is the thing we watch move. We don't watch continents flex. We don't watch the Earth's interior deform. We don't watch the sky tilt the planet's shape by fractions you'd never notice in a lifetime. But we do watch waves. We do watch shorelines change. We do watch harbors fill and empty like lungs. So the mind assigns agency to what it can see. In that simple picture, the moon is the controller and the ocean is the controlled. The moon commands, the water obeys. And twice a day, the planet politely demonstrates it. High tide, low tide, high tide again. As if the ocean is nodding along with the moon's orbit, keeping time. There's something seductive about that because it makes the cosmos feel intimate. You can stand at the edge of the sea and tell yourself you're watching gravity at work. Not gravity in a lecture hall sense, but gravity you can hear and smell. Salt in the air, wet sand under your feet, and the slow lift that arrives whether you believe in it or not. So we accept the story. The moon pulls the ocean toward itself. And if that were the whole story, tides would be almost boring. A single bulge of water would follow the moon around the planet, a moving hump always centered beneath it. You'd expect the highest tide to happen when the moon is directly overhead, like a magnet held above iron filings. You'd expect the cycle to match the moon's position cleanly, with the ocean's response lagging only a little, the way a heavy curtain lags behind your hand when you tug it. You might even expect a simple rule. Closer moon, higher tides, farther moon, lower tides, and everything else is geography and weather. But then, the world refuses to cooperate with the tidy version. For one thing, the most obvious feature of tide is also the most inconvenient one. You don't get one high tide. You get two, on opposite sides of the Earth, and not as a rare exception, but as the basic pattern you learn to draw. That alone should feel strange if the story is the moon pulls the ocean toward itself. Why would the far side of the Earth, where the moon's pull is weaker, also experience a bulge? Why would water rise where the controller is not pulling as strongly? And it gets worse. The highest tide is not always under the moon. Sometimes it happens hours later. Sometimes it happens when the moon is nowhere near overhead. Sometimes the pattern looks distorted, delayed, even stubborn, as if the ocean is refusing to respond on cue. In many places, tide charts behave like a complicated conversation between the moon, the sun, and the shape of coastlines, less like a simple tug, more like a slow argument. And here's the quietest inconsistency of all. If the moon is pulling the water up, why don't you feel anything at all? You can feel a strong wind. You can feel a passing truck shake the ground. You can feel an elevator accelerate. But you cannot feel the moon, not in your bones, not in your stomach, not in any ordinary way. Yet the ocean feels it. That gap between experience and reality is where the story starts to tilt. The simple picture is close enough to be convincing, but wrong enough to produce contradictions. It tells you what happens without telling you what is actually moving, or what is actually being pulled, or why the pattern forms where it does. Because the moon is not just pulling on water. The moon is pulling on everything. It pulls on the ocean, yes, but it also pulls on the ground under the ocean, the rock beneath the sand, the crust beneath the mountains, and the dense interior beneath the crust. The moon doesn't select water as if it recognizes it. It applies gravity to mass, and the planet has to respond as a whole, and that raises a problem. If the moon pulls on everything, why does the ocean look like the one doing all the visible moving? Why does water become the messenger? Why does the solid earth appear to stand still while the sea rises and falls? At first, the answer seems obvious. Water is fluid. Rock is solid. But that's only part of it, because solid does not mean immovable. It means resistant. And resistance is exactly where tides are born. The tide is not a wave that arrives because water was lifted like a blanket. The tide is what happens when the moon pulls unevenly on a planet that can't respond evenly. And here's where it gets strange. The controlling force is not about pulling water upward. It's about stretching the earth, subtly, continuously, while the planet tries imperfectly to hold its shape. Once you see the tide as a planet-scale deformation problem instead of a water problem, the double bulge stops being a glitch and starts being a clue. The delays stop being annoying details and start being the entire point. The ocean stops being the primary actor and becomes the most visible instrument in a system where the real motion is shared. So the simple story gets us to the shoreline, but it can't get us to the mechanism. To get there, we have to change the frame completely. We have to stop asking, how does the moon pull the water? And start asking, how does the moon pull the earth? Because the tide is not the moon controlling the ocean. It's the moon controlling the difference between what can move and what cannot. And that's the door we open next. If you want to feel how incomplete the simple story is, don't start with a textbook. Start with the most ordinary thing, a tide chart. In a lot of places, the ocean doesn't rise once a day. It rises twice. And not as a neat pair of identical peaks either. One may be higher, one may be lower. The timing can slide. The pattern can look like it's drifting forward each day, as if the ocean is chasing something it can't quite catch. That drift alone should bother you. If the moon is the controller, why is the schedule so slippery? You can stand on a beach and watch the moon in the sky, and the sea does not behave like a loyal shadow. It doesn't lift when the moon reaches its highest point. It doesn't fall when the moon moves away. Sometimes the ocean reaches high tide hours after the moon's best moment, as if the planet heard the instruction late. So which part is wrong? Is the moon not the cause? Or is your picture of cause too simple? Now look at the diagram people draw for tides. Two bulges, one facing the moon and one on the far side of Earth. The near side bulge makes sense in the naive story. If the moon pulls water toward itself, you expect some swelling there, even if it's not perfectly centered, even if coastlines distort it. The basic idea survives. But the far side bulge is poison to that story. On the far side of Earth, the moon's gravity is weaker. Not absent, just weaker. If gravity were simply pulling water toward the moon, the far side should be the most reluctant place for water to rise. And yet the simplified tide diagram says the opposite. There is also a bulge there, so you are left with a choice. Either the diagram is wrong, and tides are not actually a two-bulge phenomenon, or the mechanism is not. The moon pulls water up. And here's where it gets strange. The two-bulge pattern is real enough that you can predict it and observe it, even though the ocean and continents distort it. So you can't throw away the diagram. You have to throw away the intuition. The intuition fails because it assumes the Earth is a fixed platform and the ocean is a loose skin. But the Earth is not fixed. It's a moving body responding to gravity like everything else. This is the part the mind resists because it feels like a trick. We're used to thinking of Earth as the reference, our ground truth. We stand on it. We build on it. We assume it sits there while forces act on things around it. But in a tidal system, the reference point is part of the motion. The moon pulls on the ocean, yes, but it also pulls on the ground. It also pulls on the planet's center. It pulls more strongly on the side facing it and less strongly on the far side, because gravity changes with distance. That unevenness matters more than the overall pull. Because tides are not about the moon's gravity in general. They are about the difference in the moon's gravity across the Earth. This is why your body can't feel the moon. The moon is pulling on you, and the ground beneath you almost equally. You and the floor are being accelerated together. There's no dramatic difference at your scale, so there's nothing for your senses to latch onto. But across the entire diameter of the Earth, the difference becomes meaningful. On the side facing the moon's pull is slightly stronger than it is at Earth's center. On the far side, the moon's pull is slightly weaker, so the Earth is not experiencing a uniform tug. It is experiencing a gentle stretch, an insistence that the near side and far side should not accelerate the same way. And the Earth responds to that insistence by deforming. The crucial point is that the tide is not primarily a water rising problem. It's a planet being stretched problem. The water is just the part that flows most easily in response. But even that explanation still leaves an uncomfortable gap. If the moon is pulling the near side more strongly, you can imagine the ocean bulging toward the moon, because the water there is being pulled harder. Fine. But what about the far side? Why would water bulge outward away from the moon, where the pull is weaker? At first, people reach for the wrong word, centrifugal. They imagine Earth and moon spinning around a point, and they picture an outward flinging force that creates the far side bulge. That explanation sounds satisfying because it matches a familiar feeling from spinning rides and turning cars. But it's a trap if you use it carelessly, because centrifugal force is not an extra physical force being generated out there in space. It's a way of describing what you see in a rotating frame. It can help, but only if you keep your hand steady. The deeper truth is that the far side bulge exists because the Earth is being accelerated toward the Moon more strongly than the far side ocean is. Read that again slowly. The planet as a whole is being pulled toward the Moon. Earth's center is accelerating toward the Moon. But the far side water, being farther away, is pulled slightly less. So relative to Earth's accelerating center, the far side lags behind. It doesn't keep up as well. And that lag shows up as an outward bulge on the far side when you describe everything from the Earth's perspective. Not because water is being pushed outward by a new force, but because the Earth is being pulled inward faster than that water is. It's the same story as the coin in a curving train. From the outside, the coin travels straight while the train curves. From inside the train, the coin seems to drift sideways. Nothing pushed the coin. The frame changed underneath it. In tides, Earth's frame is changing underneath the ocean. The near side is being pulled a little harder. The far side is being pulled a little less. The result is a stretch, and the ocean reveals that stretch because it can reshape itself more quickly than rock can. And then the timing problem returns. If this is all just geometry and differential pull, why isn't the bulge perfectly aligned with the Moon all the time? Because the system is not frictionless. The ocean isn't a smooth shell. It's broken by continents, shaped by basins, dragged by sea floors, slushing with inertia. It doesn't instantly rearrange itself to match the instantaneous gravitational gradient. It overshoots, it lags, it resonates. It behaves like a massive, partially confined fluid being driven by a moving pattern. Which means the tide is not just a gravitational phenomenon. It is a gravitational phenomenon filtered through an ocean that has memory. Water doesn't teleport into a bulge. It has to flow there. It has to be pulled, redirected, and piled up against the friction and geometry of the Earth. So the bulge trails. The highest tide occurs after the Moon passes overhead, because the ocean is always slightly late. And that lateness isn't a minor detail. It's the hinge on which the next part of the story turns. Because once the tidal bulge is delayed, once it is not perfectly aligned, the Moon's pull is no longer just stretching the ocean. It is twisting it. And the moment you introduce twisting, you introduce energy transfer. The Moon begins to steal a little rotational energy from Earth. Earth's day begins to lengthen. The Moon's orbit begins to drift outward. The ocean becomes a break on a planet. All of that is hidden inside the simple story of tides, but we're not ready to pay that debt yet. First is we need a clean turning point, an observation that forces you to stop thinking in terms of the Moon pulling water up and start thinking in terms of Earth and ocean accelerating differently. Because once you adopt that frame, the two bulges stop feeling like a paradox. They start feeling inevitable. And that's the turning point we step into next. The turning point comes when you stop asking what the Moon is doing to the ocean and start asking what the Moon is doing to the entire Earth. Because the Moon doesn't reach down and grab water. It reaches into the whole planet with the same rule it applies everywhere. Gravity acts en masse. And it acts more strongly when you are closer. That more strongly when you are closer is the entire secret. Not the strength of the Moon's pull, but its unevenness. Here's a simple way to feel the difference between a force you can sense and a force you cannot. Imagine you're in an elevator. The doors close, and for a moment you feel heavy. as if your body has been pressed more firmly into the floor. Then you feel light, like the ground has softened under you. You don't need a lecture to understand what happened. You felt acceleration. You felt the reference frame change. Now imagine the elevator cable snaps, and the entire car begins to fall. This is the moment your body would stop feeling weight, not because gravity vanished, but because the floor stopped pushing on you. You and the elevator would be falling together, sharing the same downward acceleration. In that shared fall, gravity becomes invisible to your senses. There's no difference between you and your environment for gravity to announce itself through. That's the key idea. You don't feel gravity when everything around you is being accelerated by gravity in the same way. You feel gravity when you and your surroundings are being accelerated differently. Now scale that up to Earth and the Moon. The Moon pulls on the ocean, yes. But it also pulls on the crust beneath it, and the mantle beneath the crust, and the core beneath the mantle. It pulls on the entire planet. And Earth responds by accelerating toward the Moon as a whole. The planet is, in a sense, in free fall toward the Moon. Not free fall in the dramatic, plunging sense. Earth isn't crashing into the Moon, but free fall in the technical sense. Earth is being accelerated by gravity, and nothing is pushing back to hold it still. This is the part that changes everything. Because once you accept that Earth is being accelerated toward the Moon, the far side bulge is no longer a mystery. It becomes a consequence of relative motion. Think of Earth as an elevator car, except instead of falling toward the ground, it's being pulled sideways toward the Moon. Earth's center is accelerating toward the Moon at a certain rate. The near side of Earth, being slightly closer, is accelerated a little more strongly. The far side, being slightly farther, is accelerated a little less strongly. So the Earth is being stretched along the line connecting it to the Moon. Not by some special tidal force, but by the ordinary gravitational pull acting with slightly different intensity from one side to the other. That stretch has two signatures. On the near side, water and rock are pulled toward the Moon more strongly than Earth's center is. Relative to the center, the near side material is being tugged outward toward the Moon. The ocean responds by flowing and piling up into a bulge. On the far side, Earth's center is being pulled toward the Moon more strongly than the far side water is. Relative to the center, the far side material lags behind. If you ride along with Earth, if you treat Earth's center as your moving reference frame, that lag appears as an outward bulge away from the Moon, not because something pushed the water outward, because the Earth moved inward faster than the far side water did. That's the turning point. The two bulges are not competing effects. They are two sides of the same differential acceleration, and once you frame it that way, the ocean stops looking like an independent actor. It starts looking like a tracer die in a moving system. The water shows you the shape of a stretch you otherwise couldn't see. The tide is Earth's response made visible. This is why solid Earth tides exist. The crust itself flexes, rising and falling by small amounts as the Moon passes. You don't notice it because your senses are not tuned to it, and because you and the ground move together. But instruments can see it. The planet is not perfectly rigid. It yields slightly rhythmically. The ocean yields more because it can. And now the timing problem can be put in its proper place. If the tide were only geometry, if it were just a static bulge aligned perfectly with the Moon, then yes, the high tide would sit directly beneath the Moon, clean and symmetric. But the ocean is not a static shell. It's a moving fluid with inertia, flowing over a rotating Earth under a changing gravitational pattern. The bulge is not painted on. It has to be built for moving water, so it lags. The moon's gravitational gradient sets the pattern, but the ocean's dynamics decide how that pattern manifests in real coastlines. The bulge is dragged, delayed, distorted, and sometimes amplified by the shape of basins and the timing of natural sloshing modes. And here's where it gets strange in the best possible way. That lag is not a nuisance. It's the mechanism by which the moon takes energy from Earth. Because the moment the bulge is offset, when it is pulled ahead or left behind, the moon's gravity is no longer just stretching the ocean. It is exerting a torque, a twist, a gentle, persistent rotational tug, and a twist applied continuously is how you change the rotation of a planet without ever touching it. So the turning point observation doesn't just explain why there are two bulges. It explains why tides are not merely a coastal inconvenience. They are a dynamical coupling between Earth and Moon. They are the visible edge of a system that transfers energy, changes the length of our day, and slowly reshapes the Moon's orbit. But that raises a problem. If the Moon is stretching the whole Earth, and if the ocean is just the easiest part to move, then the control the Moon has is not about oceans at all. It's about planetary motion. And once you see the tide as a planet-scale response to differential acceleration, you're ready for the deeper puzzle, the part that still feels impossible even after the turning point. Because even when you accept two bulges, there is still something you haven't fully looked at yet. The fact that the bulges aren't just where you expect, they're late. And that lateness is where the real story begins. If tides were only a static response to the moon's pull, they would behave like a shadow. The moon moves, the bulges follow. Perfect alignment, clean symmetry, a planet wearing two obedient swellings that point directly at the controller at all times. But tides aren't shadows, they're late. And that lateness is not a footnote. It's the part of the system that actually does something. Because once the bulges are even slightly misaligned, the moon isn't just stretching Earth anymore, it's twisting it. To understand why that twist matters, imagine something simple, a heavy door on a hinge. If you press on the door directly toward the hinge, nothing happens. You can apply a lot of force and still fail to rotate it, because the direction is wrong. But press a little off to the side, apply a sideways push at the edge, and suddenly rotation appears. A small force produces a big effect because you found leverage. Tidal bulges create leverage. The moon's gravity is not pulling on a perfectly smooth sphere. It is pulling on a planet with raised bulges, two slight swellings of mass that are not exactly where the moon wants them to be. If those bulges were perfectly aligned with the moon would pull on them symmetrically. The net torque would be essentially zero. Stretching would happen, but no sustained rotational exchange would. But the ocean is not a rigid object. It sloshes, it flows, it drags against sea flows, it piles up against coastlines, it responds with inertia. And because Earth rotates beneath the tidal pattern, the bulges do not sit patiently under the moon. They get carried forward. This is the moment where a calm, everyday intuition breaks. Earth rotates faster than the moon orbits. In most places, the surface of Earth is sweeping eastward down to the sky. That means the ocean, attached to Earth by friction and boundaries, tends to carry the tidal bulge slightly ahead of the line pointing directly at the moon. So the bulge is not centered beneath the moon, it's offset, and that offset is a lever. Now the moon's gravity pulls on the forward-shifted bulge, and because the bulge is ahead, the pull has a sideways component. That sideways component acts like a hand placed on the rim of a spinning wheel. It is a braking force, not a dramatic brake you would feel in a day, but a persistent one you can measure over a long time. The moon pulls backward on the bulge. The bulge, through friction and viscosity and contact with the rest of the Earth, pulls backward on Earth's rotation. Earth slows, a tiny amount, relentlessly. And when Earth slows, something else must happen, because the system has to keep its books. If Earth loses rotational angular momentum, that angular momentum doesn't vanish. It has to go somewhere. In the Earth-Moon system, it goes into the Moon's orbit. The Moon is pushed outward, again, not by a rocket, not by a shove, but by the subtle transfer of motion through gravity acting on a delayed bulge. This is the deep puzzle hidden inside a tide chart. The Moon controls the oceans. Yes, but not like a puppet master. The Moon controls them like a gear, a coupling, a persistent gentle mechanism that trades one kind of motion for another. It turns Earth's spin into the Moon's orbital energy. And this is why tides are not primarily a coastal story. They're a planetary story. Once you see that, the ocean becomes almost secondary. The ocean is the visible place where friction exists, where energy can be dissipated, where lag can occur. The ocean is the interface that allows the bulge to be misaligned enough to produce torque. Without that lag, the Moon would still raise tides in a geometric sense, but the system would be far less effective at exchanging energy, so the lateness becomes the mechanism. And the mechanism has consequences that are strange when you hold them gently. It means Earth's day is not fixed. It is slowly changing. The rhythm you treat as eternal, the rotation that defines day, is being edited by the Moon. It means the Moon's distance is not fixed. It is slowly changing. The Moon you look at tonight is not the Moon your distant ancestors saw, and it will not be the Moon distant future observers will see. And it means the ocean is not just responding, it is participating. The tide is a global torque, and once you accept that, you start noticing an odd emotional quality to the system. It's intimate. The Moon doesn't need to touch the ocean to change it. It doesn't need to touch Earth to slow its rotation. It doesn't need contact. It needs only a repeating pull and a delayed response. That's enough to reshape a planet's timekeeping. But here's where it gets strange again. If this coupling depends on the bulge being offset, then the details of the ocean suddenly matter. Coastlines matter. Basin shapes matter. Depth matters. The distribution of continents matters. The internal friction of Earth itself matters. Tides are not just gravity. They are gravity filtered through the messy reality of a particular planet. So the Moon's control is not universal. It is tailored. It's tailored to Earth's geography and physics, which means the next step of understanding is not to talk about the Moon alone, but to talk about the partnership. The Moon's differential pull, Earth's rotation, and the ocean's delayed response acting together as a machine. A machine with no gears, no metal, no intention, only motion and lag. So which piece of the machine is the true cause? Is it the Moon's gravity? Is it Earth's rotation? Is it the ocean's friction? That's the trap. It's all of them coupled. And to see that coupling cleanly, we need the new framework. The one that makes two bulges, lag, and talk feel like the natural outcome of a single idea, rather than a pile of exceptions. That framework is not complicated, it's just unfamiliar. And that's where we step next. If you could shrink the Earth-Moon system down and hold it in your hands, it would feel less like a mystery and more like a device. Not a device with switches or motors, but a device with couplings, parts that don't touch yet still exchange motion, the way magnets can influence a compass needle through glass. That's what tides are, a coupling. And the cleanest framework is this. The moon doesn't lift the ocean so much as it creates a moving gravitational gradient across Earth, and Earth's rotating, imperfectly fluid surface responds with a delayed deformation. That delay turns a stretch into a twist, and the twist trades motion between Earth and Moon. Start with the one idea we've been circling. Gravity is not uniform across Earth. The Moon pulls slightly more on the side of Earth closest to it, and slightly less on the far side. That difference in pull across the diameter of the planet is what matters. It produces a subtle stretching tendency along the Earth-Moon line. If Earth were perfectly rigid, it would still be stretched, but only by an almost imperceptible amount. The whole planet would deform minutely. Instruments would notice, your senses wouldn't. But Earth isn't perfectly rigid, and it isn't perfectly fluid either. It's layered. It has oceans that can move freely, and crust that can flex slightly, and an interior that behaves differently depending on depth and timescale. So the stretching expresses itself most dramatically in the component that can rearrange itself fastest, the ocean. So the first step is deformation. The near side bulges toward the Moon because it is pulled a little harder relative to Earth's center. The far side bulges away because Earth's center accelerates toward the Moon more strongly than the far side water does, leaving that far side water relatively behind in Earth's accelerating frame. Two bulges appear. That part alone can be understood as geometry. But then you add the next ingredient. Earth rotates. Earth spins under the tidal pattern, and because the ocean is dragged by coastlines, constrained by basins, and coupled to the seafloor through friction, the bulges are not perfectly free to slide into the Moon's instantaneous alignment. They lag and lead. They become offset. Think again of the swing. The Moon is like a periodic driver, the repeating influence that tries to establish a pattern. The ocean is the driven system, a huge fluid mass that cannot respond instantly. The bulge is the response, and because of inertia and friction, the response is not perfectly in phase with the driver. That phase difference is everything. If the bulge were always centered beneath the Moon would pull on it symmetrically. The force would be mostly radial, stretching and relaxing the planet, but not twisting it in a way that systematically changes rotation. But with an offset bulge, the Moon's pull requires a sideways leverage. The Moon pulls back on the forward bulge. That pull is not strong enough to stop Earth's rotation outright, but it is strong enough to act as a long-term brake. Earth's rotation loses angular momentum. Now, in everyday life, when something loses rotational momentum, when a spinning top slows down, where does that momentum go? Usually, it becomes heat. Friction converts organized motion into disorganized vibration. Energy spreads out into microscopic motion, and the spin dies. That happens here too. The tides generate friction. Water moving across the seafloor, eddies swirling, currents rubbing against continents, and the slight flexing of Earth's interior all dissipate energy as heat. But angular momentum behaves differently from energy. Energy can be dissipated as heat and disappear into microscopic motion. Angular momentum cannot simply vanish from the system, unless something outside takes it away. In the Earth-Moon system, the outside is minimal. So the angular momentum Earth loses to tidal braking is largely transferred to the Moon's orbital motion. This is the third ingredient, exchange. The offset bulge pulls on the Moon, as well as the Moon pulls on the bulge. The gravitational interaction is mutual. As the Moon pulls backward on Earth's rotation, Earth's bulge pulls forward on the Moon along its orbit. That forward tug adds orbital angular momentum to the Moon. The Moon drifts outward, Earth's day slowly lengthens, and the system keeps running because the Moon keeps moving and Earth keeps spinning. The driver keeps repeating, the response keeps lagging, the torque keeps acting, the exchange keeps happening. That's the machine. Stretch, lag, twist, transfer, dissipate. Once you hold the mechanism in that order, the details stop feeling like exceptions. The double bulge fits. The delay fits. The fact that continents matter fits. The fact that tides vary so much from place to place fits. Because you no longer expect a clean geometric bulge painted onto a perfect sphere. You expect a dynamic response in a messy fluid on a rotating planet. You expect the ocean to behave like a half-contained slosh that's being driven by an invisible pattern. And that invisible pattern is not even purely lunar. Because the Moon isn't the only body doing this. The Sun also creates a tidal gradient across Earth. It is farther away, but so massive that its influence is significant. Sometimes the Sun and Moon align their gradients and amplify tides. Sometimes they partially cancel. Sometimes the ocean is being driven by two overlapping rhythms at once, and the coastline experiences their interference as spring tides and neap tides. You don't need a list of names or dates to feel the point. The ocean is not merely responding to one pull, it is responding to a coupled gravitational system, filtered through Earth's rotation, geography, and friction. And this is where the word controls becomes both true and misleading. The Moon doesn't control the ocean by commanding it. It controls the ocean by imposing a repeating gradient that the ocean cannot ignore. The ocean has freedom in the details, where the water piles up, how it resonates in basins, how tides peak at different times, but it does not have freedom to opt out. The Moon sets the tempo. Earth's rotation sets the phase problem. The ocean's friction and shape set the local expression. That's why tides feel predictable and chaotic at the same time. Predictable in broad rhythm, chaotic in local detail. A global driver meeting a complicated world. And here's where it gets strange again. Once you accept the framework, you realize tides are not confined to coastlines. They exist in the deep ocean. They flex the solid earth. They raise and lower the ground by small amounts. They move mass around the planet. And moving mass changes gravity very slightly. The Moon's control is not a coastal trick. It is a planet-scale conversation. And that conversation reaches into the one thing you thought was most stable, time. Because every bit of energy dissipated by tides, every tiny break on Earth's rotation, is a reminder that the length of a day is not guaranteed by the universe. It is negotiated, but that raises a problem. If tides depend on lag, and lag depends on friction and basin geometry, and Earth's geography changes, then the Moon's control over Earth's oceans is not constant across history. It evolves. So the next step is to follow that evolution. How the same simple mechanism produces different worlds depending on what the planet looks like, and how the Moon's influence becomes the long-term shaper of Earth's habitability. That's where we go next. Once you have the mechanism in your hands, Differential pull, deformation, lag, talk. You start noticing tides in places you never thought to look. Not just on the shoreline, not just in harbors and bays, but in the ground beneath your feet. Because the ocean isn't the only thing that yields. The solid earth yields too, very slightly, quietly, like a thick, stubborn material that still has to obey the same gradient. The crust rises and falls by small amounts as the moon passes. The whole planet flexes. It's not dramatic. It's not something you feel in your stomach. But it is real, and instruments see it clearly. The ground is participating in the tide the way a drumhead participates in a rhythm, even when you're focused on the sound. That alone changes the tone of the story. It means the moon's influence is not a surface effect. It's not a coastal trick. It's a planet-scale deformation that the ocean merely makes visible. And once you accept that the Earth itself is flexing, a strange question appears. If the Earth is flexing, where does that energy go? It doesn't just stretch and snap back perfectly like an ideal spring. Real materials dissipate. The interior of the Earth isn't frictionless. Every flex is a little bit of heating, a little bit of internal work. The moon is not just tugging on water, it is repeatedly kneading the planet. That kneading is subtle on Earth compared to some worlds, but the principle is the same. Repeated tidal deformation can be a heat engine, and suddenly the word control becomes richer. The moon doesn't merely control where the sea rises. It participates in controlling how Earth sheds and redistributes energy, how it responds to stress, how its shape quietly changes in time. Now come back to the thing you actually experience, the tide schedule. If the moon sets the tempo, why does the ocean refuse to keep perfect time? Because the tide is not a simple bulge that appears and disappears. It is water moving, and moving water has inertia. It has to accelerate and decelerate. It has to squeeze through channels. It has to slosh into basins that have their own natural rhythms. It has to climb continental shelves and spill into shallow seas. The result is that the tide behaves less like a shadow and more like a forced oscillation. A rhythm imposed from above meets a rhythm dictated by the shape of the container. If you've ever watched water in a bathtub after you step in too quickly, you've seen the same idea on a tiny scale. The tub doesn't fill and empty instantly. It sloshes. It overshoots. It finds its own timing. And if you keep moving in a steady rhythm, you can amplify the motion or dampen it depending on whether you're in sync. The ocean is a bathtub the size of a planet. So in some places, the tidal signal arrives cleanly, like a pulse. In other places, it resonates. It builds. It becomes dramatic. Not because the moon is stronger there, but because the geometry of coastlines and the depth of water allow the rhythm to pile up. This is why the biggest tidal ranges on Earth often happen in particular bays and narrow seas. Not because the moon targets them, but because their shapes act like amplifiers. They trap and focus the incoming tidal energy until the rise becomes extreme. The moon sets the input. Earth's geography sets the gain. That should feel both beautiful and unsettling, because it means tides are partly a property of a planet's current shape. Change the planet's shape, and you change how the moon's control expresses itself. And Earth does change its shape. Sea levels rise and fall across geologic time. Continents drift. Ocean basins open and close. Shallow seas appear and vanish. Coastlines rearrange. The container itself evolves. So the moon's tidal influence is not constant across history. The same lunar driver has been working on different ocean geometries through time, producing different tidal patterns and different efficiencies of energy dissipation, which means the moon's ability to break Earth's rotation is also not constant. It depends on how well the ocean can dissipate energy. It depends on where the friction is, how the currents run, how the bulge is shaped and delayed. The coupling strength evolves. That's a strange thought if you're used to thinking of the day as fixed. Earth's day has been different lengths across deep time, not because someone changed the clocks, but because the physical coupling between Earth's rotation and the moon's orbit has been transferring angular momentum for as long as the system has existed. The moon, in that sense, has been editing the meaning of day, not dramatically for a single human lifetime, but persistently enough that over immense time, the change is real. Now widen the picture again. Tides are also not purely lunar. The sun produces tides too. Its tidal gradient is weaker in immediate effect in many cases, but it's never absent. Sometimes the sun and moon align and their gradients add, producing larger spring tides. Sometimes they oppose and reduce the effect, producing neap tides. That's not just a calendar curiosity. It's an interference pattern. Two cosmic drivers imposing rhythm on the ocean at once. It's the same way two musicians can create loudness or quietness by aligning or opposing their waves. And once you see the ocean as a driven system under multiple rhythms, you can't unsee the deeper implication. Earth is not passively being pulled. Earth is being forced to respond repeatedly, and response always carries cost. The cost is energy dissipated as heat in the ocean and the Earth. The cost is angular momentum transferred from Earth's spin to the moon's orbit. The cost is a slight slowing of the day. And what makes it truly strange is how gentle the cause looks compared to the scale of the consequence. The moon is distant, silent, small in the sky, and yet through repetition, through lag, through talk, it has the leverage to change planetary timekeeping. That leverage is unique to Earth. It's a template. In other words, tides can be so strong that they lock rotations, forcing a moon or planet to show the same face to its partner forever. In some places, tidal heating can melt interiors. In some systems, tides can be a dominant energy source. On Earth, the moon is not violent. It is patient, but patience is one of the most powerful forces in physics. Repetition is a kind of strength. So the moon controls Earth's oceans by setting a gradient they must respond to, and by letting that response be imperfect, late, offset, frictional, so that energy and momentum can be traded. Once you see that, you're ready for proof in the most satisfying form. The tides you can measure, predict, and use. Because tides aren't just something we notice, they're something we calculate. And the fact that we can calculate them, then watch the ocean obey those calculations with eerie reliability, is one of the strongest confirmations that the framework is real. That's where we go next. One of the most convincing things about tides is that they don't just happen. They keep appointments. Long before anyone could write down the physics cleanly, coastal life learned a practical version of the truth. The sea has a schedule. Not a perfect one, not identical everywhere, but a schedule stable enough that you can plan around it, fear it, exploit it, and sometimes survive because you respected it. If you live near water long enough, you stop thinking of tides as scenery and start thinking of them as infrastructure. The difference between a safe harbor and a stranded boat can be a meter of water. The difference between a ship passing a bar and grinding itself onto sand can be a handful of inches. The difference between a calm inlet and a ripping current can be the timing of a tide turning, so people learn to predict. At first, prediction wasn't a theory. It was memory. It was tide marks carved into stone. It was repeating patterns in notes. It was the quiet knowledge of pilots guiding ships through narrow channels. If you got it wrong, the sea corrected you brutally. And over time, that practical knowledge became formal enough to write down. Tide tables emerged, not because someone wanted elegance, but because the ocean demanded it. Ports needed to know when depth would be available. Navies needed to know when currents would run strongest. Engineers needed to know when coastlines would expose mudflats or swallow them. The ocean became something you had to compute. That alone is an extraordinary fact when you think about it. The tide is a planetary-scale deformation of a fluid on a spinning Earth, driven by a moving gravitational gradient from two celestial bodies. It is shaped by basin geometry, friction, inertia, and resonance. It is not a simple system, and yet it is predictable. Not perfectly everywhere, not forever without adjustment, but reliably enough that entire economies can hinge on it. That reliability is a signature. It tells you there is a real mechanism underneath, not a coincidence of waves and weather. Weather can obscure tides. Storms can pile water on a coast and temporarily overwhelm the cycle. But when the storm passes, the tide returns to its rhythm as if the ocean were a clock that had been briefly muffled, not reset. The moon doesn't care about your storms. It keeps pulling. And because it keeps pulling, the same basic pattern keeps expressing itself. This is why modern tide prediction is not just folklore refined. It is physics welded to measurement. We track the moon's position, the sun's position, and the response of oceans and coasts. We model how tidal waves propagate through basins, reflect off continental shelves, and concentrate in narrow passages. We tune those models with observations because the world is messy. But the core driver is clean. The lunar and solar tidal gradients continue, and the ocean continues to respond. When you watch a tide table succeed, when you arrive at a harbor exactly when predicted, and see the water level match the forecast, you are watching a distant orbiting body impose structure on your local world. You are watching gravity become practical, and it doesn't stop at the shoreline. The same framework that predicts ocean tides also predicts the subtle flexing of the crust. The Earth tide is smaller, but it's there. The ground rises and falls by small amounts with lunar cycles, and sensitive instruments can detect it. If you build the right measurement system, you can see the planet breathe. That measurement matters because it turns the tidal story from something we see into something we can test. If the moon's gravity acts differentially across Earth, then the crust must flex. If the crust flexes, the timing should be coherent with the lunar cycle. If tides produce torque, Earth's rotation should show tiny, measurable consequences. If angular momentum is being transferred, the moon's orbit should show long-term drift consistent with the exchange. Each of these is a prediction, not a metaphor, and they're the kind of prediction that doesn't rely on poetic interpretation. They rely on timing and measurement. This is why the modern world can't avoid tidal physics even if it wanted to. Satellites that map Earth's shape and gravity field have to account for the moving mass of ocean tides. If you are measuring Earth's gravity precisely, you cannot pretend the ocean is static. The ocean is constantly shifting mass around the planet, and shifting mass changes the gravitational field slightly. That change can be seen. Even in space, the ocean's response leaves a trace. And this is where the story loops back on itself in a satisfying way. The moon controls Earth's oceans in the most literal sense. It creates a pattern of mass redistribution that can be measured not only by looking at water levels, but by looking at gravity itself. The ocean becomes part of Earth's gravitational signature, time-varying, predictable, rhythmic. The tides are written into the planet's field. This is also why precision timekeeping and navigation can't ignore tides. If you want to locate yourself accurately using satellites, you have to know where the ground is. If the ground is flexing and the ocean the shifting math, your reference frame subtly changes. The system must account for it. The moon and sun aren't just raising seas. They are slightly moving the baseline you measure against. Again, it's not something you feel, but it is something your technology must respect. And that's a kind of proof that feels uniquely modern. You don't have to believe the theory. Your devices behave as if it's true, because they fail if they act as if it isn't. The ocean rises and falls on schedule. The schedule depends on the moon's position. The pattern is shaped by Earth's geometry. The effects show up in measurements of gravity, ground motion, and timekeeping. The machine is real, but once you accept the machine, another question rises in a calm, almost inevitable way. If tides are a mechanism that transfers energy and angular momentum, if they are slowly changing Earth's rotation and the moon's orbit, then what are the limits? How far can that process go? Does it stop? Does it stabilize? Does it end in some final configuration? In other words, if the moon controls the oceans by turning Earth's spin into orbital motion, what does that mean for Earth's future? That's the sobering boundary we step into next. There's a gentle mistake hidden inside the word control. Control sounds like power, like an active hand. It sounds as if the moon is injecting something into Earth's oceans, like a pump pushing water around, adding energy to the system. But tides don't add energy. Tides remove usable energy. They are a brake. That's the boundary. The moon raises tides because gravity creates a differential pull across Earth. But the reason tides matter is that Earth's response is imperfect, late K, frictional, resisted. Whenever a system is driven and the response lags, you don't get a perfectly reversible dance. You get dissipation, you get heat, you get loss of organized motion. In the language of everyday life, tides are like dragging a heavy object across a floor. The object moves, but the movement doesn't stay clean. Some of it turns into warmth you can't gather back up into the original motion. Some of it leaks away as turbulence and friction. The system becomes less capable of doing mechanical work, even though the total energy is still accounted for in some form. That's what the oceans are doing with Earth's spin. Earth's rotation is a reservoir of organized energy. The planet is spinning, and the oceans are attached to that spin. When the moon raises a tidal bulge and Earth's rotation drags that bulge out of alignment, the moon's gravity pulls backward on it. That backward pull is a torque, a persistent braking torque. A brake doesn't stop you instantly. A brake changes your future. So Earth's day slowly lengthens. And because angular momentum must be conserved within the Earth-Moon system as a whole, the loss from Earth's spin largely appears as a gain in the energy is dissipated. That mismatch is the hallmark of frictional coupling. It's like a gearbox with heat loss. Motion is exchanged as, but not without a cost. The cost is paid in the ocean. Water moves against the seafloor. Currents shear. Eddies form and die. Energy becomes turbulence, then heat. The planet's interior flexes slightly, and internal friction turns some of that flexing into warmth as well. These are quiet processes, but on planetary scales and long time scales, quiet processes are kings. This is the sobering boundary. The moon's control is not a gift, it is a trade. Earth trades rotational energy for the moon's orbital rearrangement, and the ocean acts as the resistor that makes the exchange irreversible. And if you take that seriously, you can't avoid the next thought. If the moon keeps taking rotational angular momentum from Earth, and the day keeps lengthening, and the moon keeps drifting outward, does it go on forever? The calm answer is that the process has a direction, and that direction points toward a kind of synchronization, a state where the rotation and the orbit are no longer misaligned enough to keep generating the same braking torque. In many gravitationally coupled systems, tidal forces gradually push bodies toward what's called a tidally locked state, where one body shows the same face to the other. The moon is already in that state with Earth. It always shows us the same hemisphere, not because it chose to but because tides reshaped its rotation long ago. Earth is not in that state with the moon. Not now. But the same mechanism that locked the moon can, over immense time, act on Earth's rotation as well. The details are complex because the sun is involved, because Earth's oceans and continents evolve, because the system is not isolated. But the direction is not mysterious. Tidal friction tends to reduce relative motion and align rotations with orbital periods. That's what a break does. It reduces differences. So the moon's control has a built-in limit. As Earth's rotation slows, the offset of the bulge changes, the torque changes, the coupling changes. The system evolves toward a configuration where the same kind of lag leverage is no longer available. The moon cannot steal rotational energy forever at the same rate, because the very act of stealing changes the conditions of theft. And that's the deepest boundary you can feel without any equations. Tides are not a perpetual engine. They are a path toward equilibrium, a slow, frictional path, which reframes everything. The moon controlling the oceans is not just a daily spectacle. It is a long-term evolutionary force. It has been shaping the length of the day, the distance to the moon, and the thermal and mechanical life of Earth for as long as the system has existed. It is quiet control, the kind that doesn't announce itself in a moment, but rewrites a planet's rhythm over eras. And once you accept that, the last step isn't more mechanism. It's a change in how you hold the story emotionally. Because the tide you watch at night, creeping up the sand, is not merely water obeying the moon. It's time. It's the planet's spin being negotiated. It's a reminder that even the most basic human unit, the day, is not a fixed gift from the universe. It's a quantity that can be spent. And that leaves us in the final reframing, not poetic overload. Just calm wonder at what it means to live on a world where the sky can reach down and slow the ground. That's where we close. You can watch the tide at night and feel like it's just water, just shoreline drama, just the ocean being the ocean. But if you stay with it long enough, the tide stops looking like water and starts looking like time. Because what the tide really represents is not a daily trick performed by the sea. It's the visible edge of a brake acting on a spinning planet. And a brake, no matter how gentle, is always a story about the future. It changes what comes next. Earth's rotation feels permanent because it's been there your whole life. You treat the day as if it's a feature of reality, like gravity itself. But the day is not a law. It's a motion, and motions can be altered. The moon doesn't need to shout to alter it. It only needs to repeat. Each tide is a small rearrangement of mass. Each rearrangement creates friction. Each friction event bleeds away a tiny slice of organized motion into heat. You never feel that heat as warmth on your skin because it spreads through oceans and interior rocks and countless turbulent swirls. But the bookkeeper of physics counts it anyway. Over time, that bookkeeping becomes history. And it's strange to realize that the most ordinary unit in your life, the hour, the morning, the evening, comes from a spinning that is being slowly negotiated by an orbiting companion, not by intention, not by design, by geometry and friction. If you want to make the idea feel real, picture a metronome on a table. The metronome clicks with perfect confidence. It feels like the definition of regularity. Now picture someone touching the table lightly, once per cycle, always just a little late. Not enough to stop the metronome, not enough to be dramatic, just enough to introduce a tiny, persistent drag. The metronome would keep clicking, but the timing would slowly drift. That is Earth and the moon. It's one of those cosmic truths that feels almost too quiet for the scale it operates on. A distant body makes the ocean bulge. The bulge lags. The lag creates a twist. The twist drains spin, the day lengthens. No explosions, no drama. Just a slow change in what now means. And that raises a problem. If the moon can edit the day without touching Earth, what else can it edit? Because tides don't only move water. They move the entire boundary between what is rigid and what is fluid. They stress coastlines. They stir basins. They pump energy into currents and internal waves. They create rhythms that marine life learns to live with. They become a background pulse that ecosystems adapt to. The moon's control is not only mechanical, it is environmental. And once you let that sink in, the tide becomes more than a diagram. It becomes a living constraint, a schedule written into biology, culture, and survival. But if tides are a schedule, who is keeping it? The moon sets the driver, yes, but Earth's geography decides the local expression, which means the moon's control depends on the shape of the container, and the container changes. So the next layer is not just the moon changes Earth. It's Earth changes the way the moon changes Earth, a feedback loop across deep time. And that is where the story grows teeth in the calmest way. If the moon were controlling a perfect ocean on a perfect sphere, tides would be simple and timeless. But Earth is not a perfect sphere, and the ocean is not a uniform skin. It's a complicated set of basins connected by narrow passages, blocked by continents, shaped by shelves and ridges, and stirred by winds and temperature gradients that add their own noise. So the moon's gravitational pattern arrives at Earth like a clean musical note, and Earth responds like a room full of strange acoustics. Some rooms amplify, some dampen, some distort the tone into something unexpected. That's why the same moon can create gentle tides in one place and dramatic ones in another. And it's also why the moon's long-term braking effect is not a constant dial. It depends on how effectively the ocean dissipates tidal energy. Change the coastline, and you change the dissipation. Change the basin, and you change the lag. Change the lag, and you change the torque. So the moon's influence is stable in its origin, but unstable in its expression. That's a deep kind of control. The driver stays the same, but the system it drives evolves, and the outcome evolves with it. Across Earth's history, the continents have wandered. Ocean gateways have opened and closed. Shallow seas have spread across continents and then retreated. Each configuration changes how tidal waves propagate and where energy gets lost to friction. In one era, tides might have been more efficient at breaking Earth. In another, less. The same lunar pull, the same differential gradient, but a different planetary response. It means the moon has not been controlling one single ocean. It has been controlling a sequence of oceans, and each ocean wrote a slightly different chapter in the history of the day. This is where the story stops being only about physics and becomes about contingency. Because the moon's influence is lawful, but the expression of that influence depends on the details of Earth's shape, details that have changed again and again. The moon's pull is patient. Earth's surface is restless. That combination produces a world where the same mechanism can feel steady at human scale and yet evolutionary at geological scale. And that raises a problem. If the moon's tidal control depends on Earth's ocean geometry, then the tide you see tonight is not the true tide in some absolute sense. It's the tide of this particular Earth, this arrangement of continents, shelves and basins at this moment in its history, which means the moon's control is both universal and personal. Universal in physics, personal in geography. This also reframes the quiet misconception that tides are something the ocean does because it's loose. In reality, tides are something the planet does because it is not perfectly rigid. The water reveals the deformation because it moves easily, but the deformation belongs to Earth as a whole. So when the shape of Earth changes, it's not just the coastline changing, it's the planet changing how it yields. And this is the part where the tide becomes a kind of planetary fingerprint, a rhythm that tells you what the Earth is like, how deep its seas are, how its basins resonate, how its friction is distributed. If you were trying to infer Earth from afar, tides would be one of the signals you'd want to detect. They would tell you there is a nearby companion. They would tell you the planet has a fluid layer. They might even hint at the presence of continents. The moon's control leaves signatures, but if it leaves signatures, then you can ask an even bigger question. Is Earth unusual? Or is tidal control a common theme in planetary systems, quietly shaping worlds everywhere, even when there is no ocean to watch? That's the next step. Once you understand tides as a coupling, a way to transfer energy and angular momentum through lag, you begin to see them everywhere, even where there's no sea. Because the ocean is not the essence of the mechanism. The ocean is just an efficient place for lag and friction to live. Give a world any deformable layer, ice, rock, magma, even a thick atmosphere, and a strong enough tidal gradient, and the same quiet machine can run. It stretches, it lags, it twists, it dissipates. Sometimes the consequences are subtle, like on Earth. A slow lengthening of the day, a gradual outward drift of a moon, a rhythmic coastal breathing you can watch on a beach. Sometimes the consequences are extreme. If the coupling is strong enough and persistent enough, tidal forces can lock a rotation. A body ends up showing the same face to its partner, not as a mystical bond, but as the end point of a break. The moon is the familiar example. Its rotation was slowly edited until its day matched its orbital period. leaving one hemisphere permanently facing Earth. That sounds like a strange cosmic coincidence, until you realize it's just what friction does. Friction reduces relative motion. It pushes systems towards synchronized states. In other places, tides become heat, not metaphorically, literally. Repeated deformation turns organized orbital motion into internal warmth. A world that should be frozen can remain active because tides keep kneading it from the inside. This is the part of tides that can create habitability in unexpected places or destroy it. A tidally heated world can have volcanism, subsurface oceans, tectonic-like activity. It can remain dynamically alive long after it would otherwise have cooled. But it can also be overdriven, turned into a place of relentless flexing and instability. Either way, the theme is the same. Tides are not a surface detail. They are an evolutionary force. So when you ask how the moon controls Earth's oceans, you're also asking how gravity and friction collaborate to control the future of worlds. And the answer is not romantic. It's mechanical. Tides tend to spend energy. They tend to synchronize motion. They tend to reshape rotation and orbit over time. The ocean is where you can see the process with your own eyes. The ocean makes the invisible visible. But the process is bigger than the ocean. It reaches into what a day even is. It reaches into climate rhythms. It reaches into how stable a planet's spin axis might be over a long time. It reaches into whether a world stays geologically active or becomes quiet. That's a lot of consequence for something that looks like water moving in and out. And here's where it gets strange again. The moon's control is gentle enough to feel harmless, but strong enough to matter. It sits in that rare zone where a force is not catastrophic, yet not negligible. That zone is where long-term shaping happens. Too weak, and nothing changes. Too strong, and everything breaks. Earth and moon have lived in the shaping zone, which means the moon's influence on Earth isn't an accident of beauty. It's a structural relationship with a timescale long enough to write history, but that raises a problem. If tides are a break and a shaper, and if systems evolve towards synchronization, then what does the Earth-Moon system evolve toward? Not tomorrow, not in any near-human sense. In the long run, what is the quiet destination of a world whose oceans are coupled to an orbiting companion? That's the next run. The Earth-Moon system has a direction, not a prophecy, not a prediction about dates on a calendar, but a tendency carved into the mechanism itself. If the bulge lags and creates torque, rotation energy is drained, angular momentum is exchanged, and the system shifts. So the natural question becomes, what does shift mean in the limit? It means Earth's rotation continues to slow in the sense that the day lengthens. It means the moon continues to drift outward in the sense that its orbit expands. It means the coupling continues until the conditions that make the coupling effective begin to change. Because the mechanism is self-modifying. As Earth's rotation slows, the amount by which the bulge is carried ahead changes. The phase relationship shifts. The torque changes, the efficiency changes, the ocean's resonance with the driver changes. So the system is not marching toward a simple endpoint at a constant rate. It is evolving along a path where the rules remain the same, but the parameters drift. And the endpoint, in broad terms, is a more synchronized configuration, less relative motion, less ability for the moon to apply the same braking leverage. In a perfectly isolated, perfectly frictional two-body system, The long-term tendency is toward a state where the same face is always presented both ways, mutual tidal locking, a quiet, synchronized pair. Our system isn't that simple. The sun is there, other planets exist, Earth's geography evolves, the ocean's shape changes, the interior responds differently across time. But the tendency remains. Tides reduce differences, trade motion, and dissipate energy. So the moon's control has a built-in narrative arc. It begins with strong relative motion, a fast-spinning Earth, a closer moon, intense coupling. Over time, that relative motion becomes less extreme. The day lengthens, the moon moves outward, the coupling changes. And if you hold that gently, you realize something intimate and strange. We live at one moment in a long negotiation. The day length you experience is not eternal. It is a snapshot. The moon's distance is not eternal. It is a snapshot. The exact tidal patterns you watch are not eternal. They are snapshots of a living system. The moon is not simply controlling the oceans, it is participating in the slow editing of Earth's rhythm. And that makes tides feel less like a coastal routine, and more like a visible clockwork of deep time. A clockwork that doesn't tick in seconds, but in friction and orbit. But that raises a final problem. If the moon's control is real and measurable, and if it has shaped Earth's timekeeping, then why does it feel so easy to ignore? Why can you go your whole life without thinking about it, even though it's rewriting the day? The answer is scale. Tidal control is the kind of influence that is too small for your senses and too large for your patience. It lives in the middle distance between the instant and the eternal. It takes an ocean to show it, and it takes time to prove it. Which is why the shoreline is such a perfect place to understand it, because the shoreline is where cosmic gradients become local motion. Where an invisible differential pool becomes wet sand and shifting water. Where the moon's gravity becomes something you can see without believing. And that is the calm, existential reframing waiting behind the science. Not that the moon is powerful, but that the universe does not need loud forces to change a world. It only needs repetition. Which brings us to the last block, the final reframing that ties control, patience, and human-scale wonder together without turning into poetry overload. So if you ever want to understand what control really means in physics, don't look for a hand pushing. Look for a small difference that repeats. That's what the moon offers Earth, not a shove, but a gradient, a slight unevenness in gravity across a planet. A gentle insistence that near and far, here and there, cannot accelerate exactly the same way. The ocean responds because it can. It flows, it piles up, it lags, it turns geometry into motion. It turns an invisible pattern into something you can watch with your eyes. And then the deeper layer appears, because the ocean doesn't just move, it resists, it rubs, it dissipates. It turns a clean gravitational drive into heat and turbulence. It creates a delayed bulge, and the delayed bulge becomes leverage. So the moon doesn't merely raise tides, it extracts time from Earth's spin, not as theft in a moral sense, just as physics in its most honest form. A trade, a transfer, a system keeping its books. The strange comfort in this is that nothing in the story requires drama. The universe doesn't need violence to reshape a world. It only needs persistence and a place for friction to live. A tide is a daily reminder of that. You can stand on a coast at night, hear the water moving, and understand that the driver of the motion is not the wind and not your imagination, but a distant companion in orbit, a body that never touches the sea, yet still drags it into rhythm. And if you hold that long enough, you notice something that feels almost like a moral of the cosmos, except it's not moral at all. It's structural. Small differences matter when they are allowed to repeat. Friction matters when it has time. The future is shaped by what doesn't cancel. That is how the moon controls Earth's oceans. It controls them by being consistent, by imposing a pattern the planet can't quite follow perfectly, and by letting that imperfection do work. The ocean becomes the place where the universe turns a gradient into a story. And the story is not only about water. It's about what kind of universe we live in. A universe where you can change a planet today, not with a catastrophe, but with patience. Where the most powerful forces are often the ones that act quietly, repeatedly, and without needing your attention. So the next time you hear the tide, you can hear it as a coastal routine, or you can hear it as the sound of a system keeping its books. Earth spinning, the moon orbiting, the ocean lagging, energy dissipating, angular momentum trading hands, a silent machine running in plain sight. And in that machine, there's a final calm truth that never really leaves you once you see it. The moon doesn't have to lift the ocean. It only has to pull unevenly, and the oceans do the rest. If you've been holding the mechanism in your mind, differential pull, deformation, lag, torque, there's still one place your intuition will keep trying to rebel. It will keep trying to picture the tide as two smooth humps of water traveling around a perfect Earth, like a pair of obedient shadows. That picture is useful for exactly one thing: understanding that there are two tidal bulges in principle. After that, it becomes a kind of lie that refuses to die because the real ocean doesn't behave like a clean shell. It behaves like a restless one sloshing, partially trapped fluid, driven by a rhythm that never pauses. So the last aha is this: the moon controls the oceans with a clean gravitational pattern, but the ocean answers with a complicated voice. The moon's tidal forcing is global and repeatable. It arrives like a steady beat, but the ocean is not a single instrument. It's an orchestra split into basins, each with its own acoustics, each with its own natural ways of moving, each with its own friction, depth, and boundaries. So the same lunar rhythm can produce very different results depending on where you're standing. That's why someone can grow up near one coastline and treat tides as a gentle background, while someone else grows up near another coastline and treats them as something that can rewrite roads and swallow harbors. It isn't because the moon is more present over one place than another. The moon's differential pull across Earth is the same kind of pattern everywhere, changing smoothly with latitude and geometry. The difference is that the ocean is not obliged to produce a single global bulge that cleanly tracks that pattern. The ocean is obliged only to respond, and it responds through the laws of fluids and the geography of Earth. To see why, forget the moon for a moment and imagine a simple everyday experiment. Fill a long bathtub. Tap one end rhythmically with your hand, very gently, with a steady timing. You'll see waves travel, reflect, interfere, and sometimes create spots where the water level barely changes, even while the ends are sloshing. You'll see that the response is not a bulge that follows your hand. It's a pattern of motion shaped by boundaries, inertia, and resonance. Now replace the bathtub with an ocean basin and replace your hand with a moving gravitational gradient. The principle is the same. The forcing is steady, but the response is complicated. A tide is not a static lift. It's a wave-like motion. The moon's differential pull continually tries to deform the ocean, and the ocean responds by sending tidal waves through basins. Those waves travel around continents, bounce off shelves, and interact with the rotating Earth. They don't settle into a simple hump, because the forcing never stops long enough for the ocean to relax into a static shape. And Earth's rotation adds another twist, literally. On a rotating planet, moving fluids don't take straight paths in the way your intuition expects. The rotation introduces deflection tendencies that shape how large-scale flows organize. That doesn't mean the ocean is confused. It means the ocean is obeying the rules of motion in a rotating frame. The tide becomes not just an up and down motion, but a circulating pattern, a kind of rotating tide system in many basins. This is why, in the real world, the tide pattern often looks like it's pivoting around certain locations, rather than forming a neat global bulge. It can create regions where the tidal range is small, and surrounding regions where the tidal range is larger, like a slow spinning wave sweeping around a point. The ocean's response organizes into rotating patterns, because that's what large basins on a rotating Earth tend to do under periodic forcing. Once you see that, a lot of weird tide facts stop feeling random. Why do some places get huge tides? Because the basin shape and depth allow the forcing to line up with a natural sloshing rhythm. It's like pushing the swing at the right moment. The ocean doesn't need a stronger moon. It needs the right tying and geometry. Why do some places get surprisingly small tides? Because the tidal waves can cancel, interfere, or fail to build in that local geometry. It's like standing in a room where a sound wave creates a quiet spot, not because the speaker is silent, but because the room shapes the sound. Why do tides peak late relative to the moon? Because water has inertia and friction. It has to move. It doesn't teleport into the bulge. In many basins, the maximum sea level occurs after the maximum forcing because the system takes time to respond. That lag isn't a defect. It's how the ocean reveals the presence of dissipation. And dissipation matters, because dissipation is what turns a pretty celestial rhythm into a torque that can slow a planet. In other words, the messiness of real tides is not just messy. It is the entire point. A perfectly frictionless ocean on a perfectly smooth Earth might produce an elegant, perfectly aligned response with minimal lag. It would still deform under the moon's gradient, but it would be far less effective at converting that deformation into heat, turbulence, and long-term rotational change. The real Earth, with rough seafloors, complicated coastlines, shallow shelves, and basins that resonate, is far better at producing the lag that allows the moon's pull to act like a brake. The ocean is not merely being controlled. It is the mechanism by which control becomes consequential. Now bring the sun back into the picture, because the end of a story is often where you notice the hidden second character. The sun also produces tides. And because the sun's tidal forcing comes in with its own rhythm, the ocean is being driven by two overlapping beats. Sometimes they reinforce, sometimes they partially oppose. The result is the familiar pattern, where certain alignments create larger tidal ranges, and other alignments create smaller ones. But if you look at it with the framework you've built, it becomes something richer than a calendar curiosity. It becomes interference, two periodic drivers producing a combined response. It becomes a slow breathing of forcing strength, layered on top of the daily rhythm. And because the ocean is a complicated resonance system, those changing strengths can interact with basin dynamics in ways that make local tides feel surprisingly alive. This is also why tides come with currents, not just water levels. As the tidal wave passes through a basin, water must flow. Narrow channels become accelerators, inlets become pumps. Some of the most powerful currents you can encounter in the ocean are tidal currents in constrained passages. They're not random. They are the necessary motion of water, trying to satisfy a periodic rise and fall constraint in a container with bottlenecks. So, the moon's influence appears not just as height but as motion, and motion is where friction lives. This is the deep loop that makes the whole story close on itself. The moon imposes a pattern. The ocean responds with motion. The motion loses energy to friction. The friction produces lag. The lag creates torque. The torque transfers angular momentum. The day lengthens. The moon drifts outward. The forcing pattern slowly changes as distances change. The ocean's response continues, never perfectly the same, always shaped by Earth's evolving geometry. The moon controls the oceans, but the oceans also control how that control expresses itself. That's why the story is so satisfying when you stop demanding a clean diagram and start letting the world be the world. It also explains why tides have always been a kind of quiet test of human humility. You can know the moon is the driver and still be surprised by what happens at a particular coast. You can understand the physics and still misjudge a harbor if you ignore local geometry. You can see the global mechanism and still be reminded that a planet is not a toy model. And if you needed one final reason to take tides seriously as a planetary story, it's this: we can measure them, predict them, and model them with astonishing success. But we do so by respecting both sides of the relationship. We respect the clean cosmic forcing, and we respect the messy earthly response. That balance is the real lesson hidden inside the moon's control. The universe provides a simple rule. The world provides a complicated surface. The resulting behavior is neither pure simplicity nor pure chaos. It is structured complexity. And once you recognize that, you're ready for the final landing. Because the most important part of the story is not that the moon can move oceans. It's that it can do it without ever touching them, using only an uneven pull and the patience of repetition. Which means the control is not loud, it is quiet, and it is constant. And that is exactly the kind of force that shapes a world over time, while you're busy living inside a single day. There's a particular kind of power that doesn't look like power at all. It doesn't arrive with force. It doesn't announce itself with noise. It doesn't break things quickly enough for your instincts to respect it. It simply repeats. It returns. It insists. And it waits for the world to reveal where it cannot respond perfectly. That is the moon's grip on Earth's oceans. Not a grip like fingers. A grip like a pattern. A gentle gravitational gradient across a planet that never stops rotating, never stops carrying water, never stops dragging that water through channels and over rough sea floors. A pattern that the ocean cannot ignore, but cannot follow perfectly either. The moon doesn't need to lift the sea like a hand lifting a sheet. It only needs to pull unevenly, and let the ocean do what oceans always do. Move late, move imperfectly, and lose energy in the moving. Because that imperfection is where the real control lives. You can feel the temptation to call it just tides, as if tides are a decorative feature of Earth, like clouds, like waves, like weather, pretty, changeable, local. But tides are not merely local, they're planetary. They're a global deformation problem made visible by a fluid layer. They are the Earth-Moon relationship written onto the surface of the world twice a day. And what makes that relationship truly strange is that it operates at two scales simultaneously. At the human scale, it's a rhythm, a schedule, a predictable rise and fall that fishermen learn, that harbors depend on, that coastlines display like a daily breath. At the planetary scale, it's a transaction, a slow exchange of angular momentum, a long-term breaking of rotation, a mechanism that literally changes what a day means, not because anyone redefined the clocks, but because the planet's spin is being edited by the sky. Those two truths are the same phenomenon, just viewed through different windows of time. Stand at the shore and you see a tide. Step back through centuries and you see Earth's rotation slowly shifting. Step back further and you see a moon drifting outward, the system reorganizing itself toward a calmer relative motion. The same gentle pull, the same lag, the same dissipation, the same bookkeeping. This is where the word controls becomes both accurate and incomplete. The moon controls the oceans because it sets a forcing pattern they must respond to. The oceans cannot opt out. They can only respond with the tools they have: flow, inertia, friction, resonance. But the moon also depends on the oceans to make that control consequential. Because without friction, without delay, without a bulge carried forward by Earth's rotation, the moon's pull would stretch the Earth and then give back the energy almost cleanly, like an ideal spring. It is the ocean's refusal to be ideal that turns the stretch into a twist. And the twist is where worlds change. That sounds abstract until you anchor it in something you already understand: pushing a swing. If you push a swing at exactly the right moment, you add energy. If you push at the wrong moment, you take it away. Timing matters because the swing is an oscillator and your force is periodic. When timing is offset, you can either feed motion or drain it. Earth's rotation drags the bulge ahead. The moon pulls back on it. The timing is such that the system drains Earth's spin. The ocean is the medium that allows the phase difference to exist and persist. The moon's gravity is the periodic driver. The tide is the visible oscillation. The dissipation is the reason the story has an arrow of time. That arrow points one way, toward less relative motion, toward a calmer mismatch, toward a configuration where the moon's leva loses some of its leverage, because the planet's rotation has been slowed and the bulge's offset changes. So the moon's control is not just about making water rise, it is about making the future different from the past. And in that sense, the moon is not merely a companion in the sky. It is part of Earth's long-term stabilization system, quietly shaping rhythms, exchanging motion, and enforcing the universe's preferred behavior. That differences are smoothed by friction when given enough time. But now return to the paradox that makes your thumbnail work. A small bright moon hovering over a huge ocean world, as if it's puppeteering the planet. The paradox lands because your instincts want to reject the scale mismatch. How can something that looks so small from here be responsible for something so large down here? And the answer is that scale in the sky is not scale in physics. The moon doesn't need to be large to matter. It needs to be consistent. It needs to apply a differential pull across a large body. It needs a partner that rotates and has something that can lag and dissipate. Once those conditions exist, control is not about size. It's about geometry, about repetition, about the fact that a tiny gradient across a world can drive enormous flows when it acts on a fluid ocean, and that those flows can become a torque when they are delayed. That's the real lesson hidden under the tide line. The universe is not shaped only by violent events. It is shaped by small differences that get to repeat. It is shaped by friction that gets to work. It is shaped by systems that can't respond perfectly, and therefore must pay a cost. A coastline is where you can watch that cost being paid in real time. Water rises, water falls, current turn, and energy becomes turbulence and warmth, uncollectible again. And far above, the moon continues on its orbit, never touching the sea, never pausing, never needing to do anything more dramatic than exist. So if you want a final clean frame to hold in your mind, it's this. The moon controls Earth's oceans the way a metronome controls a room full of objects perched on a shaky table, not by moving them directly with a hand, but by imposing a rhythm that they can't perfectly follow until their imperfect response becomes motion. The control is not domination, it is constraint, and constraint, repeated long enough, becomes history. But that raises the last gentle question before we close the door. If the moon's control is really a story about gradients and patience, if tides are a daily reminder that the sky can shape the ground, then what else in your life feels stable simply because it changes too slowly for your senses to notice? That's the quiet place the conclusion will land. So now, with the mechanism understood, the paradox resolved, and the boundary clear, we can do what this channel always does at the end. We return to the simple thing, and we let it feel huge, and then we let it go. The moon pulls the oceans. That's the simple thing we started with, the kind of sentence that feels like a trivia fact you can repeat without really touching it. A line you could carry to the beach and forget as the water comes in. But now you can feel what it actually means. It means the Earth is not a rigid stage with a liquid decoration on top. It means the entire planet is being stretched by an uneven pull, and the ocean is simply the part that can answer most visibly. It means the tide is not a wave the moon sends, but a deformation the planet keeps trying to complete, late, imperfectly, because the forcing never stops and the world is never frictionless. And when a response is late, it becomes leverage. So the tide is not only a rise and fall, it is a torque, a quiet twist applied to a spinning world. A transaction that turns some of Earth's rotation into heat in the ocean, and some of it into the moon's outward drift. A reminder that even the length of a day is not a gift handed down unchanged, but a quantity that can be spent. That's the boundary hiding inside the beauty. The moon doesn't need to touch the sea to control it. It only needs to pull unevenly and to pull again and again and again. Given a fluid layer that can lag and a planet that rotates, repetition becomes power. Small differences become motion. Motion becomes friction. Friction becomes history. If you're still here with me, take a second to like the video, subscribe, and leave a comment telling me where you're watching from and what time it is. I love seeing how far this little nighttime journey reaches, and now we can close the door gently. The moon pulls the oceans. The oceans answer, and the world keeps time.